Hey guys, my name is Kevin from the University of Maryland.
Hi everyone, super excited to be here. My name's George. I did all this work at the University of Maryland, and now I work at MSRC for Microsoft.
Just want to give a huge shout out to all the BlueHat organizers, all the techs, and just all the... Great job, guys. And all our co-collaborators who couldn't be here to do this with us. We often get asked at events like this, why study censorship evasion, like as a security researcher? Because isn't this a solved problem? Like, sure, censorship happens, billions of people are censored, but we have Tor, we have VPNs, we've got secure HTTPS. But that's just the thing, right? Because we have all these things. But there's countries around the world actively working to block these services, degrade these services, or man in the middle of these things. And this is just to name a few. So censorship still affects billions of people around the world. What we're here today to talk to you guys about is Geneva, which is our effort to defeat censorship everywhere. So we're bug hunters, but doing it a little differently. Our goal is not to get shells or to compromise machines. So we're super excited to be here and tell you about this work. It really has the potential to change things up, we think, in the censorship arms race. But before we get started and talk about Geneva, defeating censors, or bugs and great firewalls, I want to take you guys through a little bit how censorship is operated today. So there's many types of censorship around the world. But some of the most pervasive is this type of automated in-network censorship run by nation states. Now, some nation states operate censorship like this, and this is often what people picture when they see censorship, where the censor is physically inside the network path. In practice, though, it's often difficult for censors to get machines on all the paths. So instead, the way many nations do this is a little like this, where the attacker is on the path, not in the path. So instead of being a man-in-the-middle attacker, they're a man-on-the-side attacker. And there are some really interesting implications to how censorship is performed when you have an attacker like this. So let's see an example. Here we have a client, let's say in China, and he's about to make a request to some forbidden resource. So let's say Wikipedia. Okay? And here's his request, and it's going to move through the network. All right? So the request will go through, and even though Wikipedia is a forbidden resource, the server will still get a packet. The censor will just get a copy of the packet. So if the regime wants to censor the connection, they can't just drop it, because they're not in the path. So instead, what the censor will do is it will inject its own traffic into the connection stream. And specifically, it's going to inject spoofed TCP teardown packets. Okay? Now, these are normal packets. Our computers send these all the time. And the purpose of these packets is basically just to say, don't talk to me. And the censor is going to send two of these. It's going to send one to the client, pretending to be the server, and it's going to send one to the server, pretending to be the client. All right? Now, both sides are going to get this packet, and the client is going to see it, and it's going to say, oh, looks like the server just shut down our connection. And the server is going to say, looks like the client wants to stop talking to me. And both sides will immediately stop talking to each other, and just like that, censorship has been achieved. Okay? But if you think about this, as the censor, you need some information about the connection to pull this attack off. Right? You need to know the sequence acknowledgement numbers, you got to know the source port, destination port. So you actually need to be tracking per flow state of the connection. So to do this at the censorship scale, if you're trying to pull off this attack, you need to be tracking the state of all TCP connections coming into and out of your country. And if you are trying to track the TCP state of every single connection coming into or out of a country the size of the nation of China, you're going to necessarily have to take some shortcuts or write bugs along the way. And we as evaders can take advantage of these shortcuts. So let me walk you through an example of what this can look like as an evader. This is from prior work that researchers have found in the past. So once again, our client is about to make a request, once again to Wikipedia. But instead, what we're going to do before we send our request is the client's going to inject its own packet into the connection stream. Okay? And it's going to send its own TCP reset. But we're going to send it in such a way that we set the TTL, or time to live. Now, this is a measure of how long the packet survives in the network. It decrements once per hop. We're going to set the TTL high enough such that it reaches the censor, but not high enough to reach the server. Okay? So we'll send this packet just like before. So if you'll notice, just like before, the censor gets a copy of the packet. Okay? But the server won't. It gets dropped along the way. So at this point, the censor sees this packet and says, looks like the client just terminated its connection. I can stop tracking it now. And it throws away the state it's maintaining of this connection. And at this point, now we're free to communicate client and server for the rest of this flow free of censorship. Because the censor has no state with which to censor us, and the server never even knew we pulled off this trick. This is one of these cool ways that researchers in the past have found to defeat censorship. Now, unfortunately, we've come up with many of these type approaches, but most of them no longer work. Most of them have been killed off over time. And it kind of comes down to how we've always done this research. Here we go. Because historically, the way research in this space, and just us as researchers have always approached problems like this, has always looked a little like this. We take hypotheses, we make hypotheses, we take measurements, and we iteratively work to build up a good mental model of how the sensor operates. Okay? And then once we do that and have our good understanding, we apply some of our good training in human intuition, and we make some tool, we put out some blog, and we defeat censorship. But of course, then the censor goes ahead and downloads our tool and reads our paper and sees our blog, and they update themselves. And we've been at this disadvantage to censors from the beginning, because to us, censors are a black box. We don't get their code. We don't see how they operate on the inside. We can only poke them from afar. So it's much faster for censors to update themselves in most cases than it is for us to do this largely manual process of understanding, taking measurements. This has put us at a big disadvantage historically. So we saw this problem, and kind of the genesis for this work was to try and give evaders the advantage instead. Okay? So the model we're here to tell you guys about today is going to turn this on its head a little bit. And our model looks a little something like this. So we're proposing automated or AI-assisted censorship evasion research. So step one is you take some AI, fuzzer learning algorithm, and you just point it at the server and you let it rip. And at step one, let it run at machine speed and defeat censorship at machine speed. At that point, at step one, we can now put what the AI has found out to the world, and people can use what it has found to defeat censorship. So we can defeat censorship at machine speed, but censors must still update themselves at human speed. And then after the fact, we as researchers can go back and look at what the AI has found and identified, and then update our mental models after the fact and say, well, this strategy worked, so the sensor has to work like this. This one didn't, so the sensor's changed recently. Okay? We can do this after the fact. Now, this sounds ridiculous. We've actually built and deployed the system. We've built it as a genetic algorithm, which we call Geneva, standing for genetic evasion. So for the rest of this talk, I'm going to take you through how we designed and built Geneva, some of the challenges in setting that up. And then we're going to take you through how we ran Geneva and some of its results against real-world sensors around the world. So, Geneva is a genetic algorithm, which is a biologically inspired system. And I'll walk you through what genetic algorithms can look like just using us humans as samples. Okay. If you want to build a genetic algorithm, there's a couple things you need. And the first is building blocks. So for us as humans, our building blocks are just these DNA bases, right, ACTG. And alone, they can't do too much. But when you have some way to compose them, like to our DNA or RNA, suddenly they become much greater than the sum of their parts. So you need some starting point, some building blocks, and some way to put them together. Next, you need some way to mutate them or mate them, and that happens for us just between generations. And finally, some fitness metric to answer the question of which individuals are fittest, which should survive to the next generations. Okay? So there are a couple challenges in this setup in applying this to a problem like censorship evasion. So let's take a look at building blocks. Okay? Now we want Geneva to run strictly at the client. Okay? So basically what it's going to be doing is manipulating packets and manipulating the packet stream coming into and out of the client. But this already at step one raises some pretty big questions. Because if you think about it, there's a lot of ways you could give an algorithm abilities to change packets. So for example, on one hand, we could let it just manipulate any bit. Just give the whole packet as a stream of bits and let it change anything. This would be super versatile, right? In theory, it could learn anything. But you can imagine it taking forever just to learn something like a checksum. So in practice, we find this is not such a great idea. Now on the other hand, if we want to really go in on speed, we could encode it with some known strategies. So for example, that TTL limited reset I showed you at the beginning. We could encode things like that as building blocks. This would be highly efficient, right? You'd be able to find things much more quickly. But the downside is we would be encoding our own human bias into it. We'd be forcing it to look in spaces that humans have already explored and would really let it explore no more. So what we land on here is letting Geneva do what IPv4 does to your packets normally. Okay? So we give it 4 building blocks. And these are duplicate, tamper, fragment, and drop. So duplicate is exactly what it sounds like. You take one packet, you have 2 packets now. Tamper is you have 1 packet, you change it in some way. Fragment, you take 1 packet and it makes 2 packets. And drop, you take the packet and you drop it on the floor. It goes away. Now I'll call out two things specifically here. For fragment, we let it alter or corrupt any TCP/IP header fields. And importantly, we're not encoding any semantic understanding of what these fields mean. So Geneva can change the flags field, and it sees that as a field of bits it can manipulate, but it doesn't have any understanding that if I set this to a SYN, that means the start of a connection. And then after it does that, we'll go back and make sure the packet is syntactically correct. We'll update the checksums, the lengths, etc. I'll also call out fragment here. It does a bit of double duty. At the IP layer, it can fragment packets. At the TCP layer, it can segment the packets. Okay. So at this point, we have our building blocks to work with. Now we just need a way to put them together. If you look at these building blocks, they kind of give us a nice way to put them together. Tamper, you take one packet and you end with one packet. But duplicate and fragment, you take one packet, you end with two packets. So what we can do is start composing these things into a tree structure. And that can look a little something like this. Okay? So we can put these actions together. At the top of our tree, we have a duplicate. If it sees a packet, it will take it and duplicate. To the left side, it won't do anything. To the right side, it will tamper it by changing the TCP flags and then set the TTL field. Now, the last thing we need with this composition, now that we have a way to compose these actions, is to decide when to run them, right? We don't want it necessarily to just run on everything. So lastly, we encode this idea of a trigger, and that's this thing at the top. So this trigger here is any outbound TCP packet that has the flag field set to ACK, an exact match. It will capture that packet and run this tree. So let's see what this looks like in practice. So once again, we've got our client. He's about to make a request to the server, and he's just about to finish the three-way handshake. So he's about to send an ACK packet. Now Geneva will identify that this packet matches an active trigger, and it will pull it into the tree. It will duplicate the packet. The left side is done, so it won't do anything further. On the right side, it changes the flags field to reset, sets the TTL. Then we do an in-order traversal of the leaves and send the packets. So we send the first one, we send the second one, and we're done. And if you'll notice, this tree exactly captures the strategy I opened this talk with, right? This here is a TTL limited reset attack. And in fact, we find that this structure is expressive enough that we were able to go back to all prior work in this packet manipulation space and re-express those strategies in these type of trees. So now we have a way to compose these actions together and use them for the genetic algorithm. Next, mutation, and this is actually the easiest one, because there's so many different ways we can mutate these things. You can change types, switch actions out, swap subtrees. If you're interested in the full list, it's available on our paper of the mutations we exposed to Geneva. Lastly is the fitness metric. And fitness is basically trying to answer the question, which individuals are fittest? Which should survive to the next generation and propagate? Okay? And it basically comes down to, in a genetic algorithm, what behavior do we want to reward, and what behavior do we want to punish? And specifically what we land on looks a little like this. We punish it very strongly if it doesn't trigger in any packets. So we encourage it to find triggers that are precise and operate. Next, we punish it a lot if it breaks the underlying TCP connection. We want to encourage it to search the space of strategies that keep the underlying TCP connection alive. Of course, we reward it very much if it successfully obtains the forbidden content and defeats the censor. At this point, we could be done, right? This alone would be good enough to work. But the AI could go and run and learn some enormously complicated thing. But we as researchers, we kind of want to understand what that enormously complicated thing is doing. So lastly, we give it one more reward for making the strategy concise and understandable. So it can run, it will find something, and then trim it down so us humans can understand it more easily. So this, in a nutshell, is Geneva. We're now ready to start taking this thing and running it against real-world censors. So I will turn it over to George to show you about some of the results Geneva's found.
Thank you so much, Kevin. We deployed Geneva in 3 different countries, China, India, and Kazakhstan. And I'm going to take you through some of the really cool technical details of the strategies we found. But before we can do that, we need a better grasp on what censorship looks like in these 3 countries so that we can understand the strategies themselves better. It works over several protocols, including FTP, DNS, HTTP, and more. And this works exactly like Kevin said earlier. It's just injecting TCP resets into both sides of the connection. By contrast, India is the least sophisticated of the 3 censors. We think this is due to the fact that India's censorship actually works on a per ISP basis. So each individual ISP is building their own censorship system. And what we found here is they just take a look at the HTTP request and they take out the host header. If that host header is a blocked page, then they'll censor the connection just by injecting into the HTTP stream a block page. Finally, we have Kazakhstan, which works over HTTP and HTTPS. Their HTTPS system is actually super interesting, and the way this works is it sits in the middle of the connection, and whenever it wants to censor the connection, it will inject a fake response using a DNS root certificate and black hole the remaining traffic. Geneva was really, really good at finding strategies in these three countries. In fact, it was so good that we needed a better way to explain them. So we created this thing called a taxonomy. Our taxonomy has three separate tiers: species, subspecies, and variants. And I'll take you through this real quick. So we call a species like the underlying bug or overarching, it's more of a class of bugs in a way. And Geneva can exploit an individual bug in several different ways. Each way we call a subspecies. Finally, each functionally distinct strategy we call a variant. In China, we found 31 such variants. In India, we found 6. And in Kazakhstan, we found 13. Now, I realize this doesn't add up to 36. I can do math. I can add. The reason for that is some of the strategies that work in China will also work in other countries. So there's a little bit of overlap between the two. I'd now like to take you through some really cool strategies on the client side that we're excited about. The first one is called the turnaround species. This isn't something crazy new that Geneva found. In fact, this worked about 5 or 6 years ago in China, but it works in Kazakhstan today. The way this strategy works is we take a SYN packet, so this is just at the start of the connection, and we duplicate it. To that first duplicate, we change the flags to SYNAC, and then we send a normal SYN as is normal in TCP. The way this looks to the server is it gets the SYNAC packet in, and it says, I don't have a corresponding connection for this SYNAC. This isn't TCP compliant. I don't know what to do with it. Let's drop it on the floor. Then it sees the normal SYN come through. It says, all right, this makes sense. I know what to do here. Let's move forward with this connection. But that's not what happens at the censor. Instead, the censor sees this SYNAC packet and thinks, oh my god, I must have somehow missed a SYN packet. And the only way that a SYNAC packet could be coming through the connection is if it's coming from the server. But remember, that's not the case. Here, we're the client. So now we've successfully reversed the roles of client and server in the minds of the censor. And this is actually enough to get around censorship in Kazakhstan because it needs to differentiate packets that come from client and server because it has to handle them differently. Let's take a look at a little bit of a more complex species. This one is called the segmentation species. And this works in China today. This is actually a really, really cool strategy because it's highly surprising that it exists at all. And this is completely new, something Geneva's found. The reason this is so surprising is because China has been able to reassemble packets now for nearly a decade. And all we're doing here is splitting this packet up twice. So we take a normal HTTP request, something that looks like this, get question mark search equals ultrasurf, and we split it up twice. And ultrasurf is just like, it's a popular circumvention tool China doesn't want us to know its citizens about. Okay, so we're splitting this up twice, and when I'm first thinking about this, I think maybe what we're doing here is somehow splitting up ultrasurf along different packets, and the censor can't put those packets back together, and then it gets confused. But that's not the case. Check this out. The way that we split up these packets is such that ultrasurf is held entirely in one packet. And remember, this is sent in plain text on the connection. It's just right there. Anyone can see it. It's in order. It's very easy for the censor to see it and censor the connection if they want to. These are sent in order. And we found a couple of interesting constraints that we found about this. The first constraint is that the first packet must be less than or equal to 8 bytes long. And the second constraint is that the sum of the lengths of the first 2 packets must be greater than or equal to 12 bytes long. There's a couple of interesting constraints that are additional. If you're interested, please read our paper, come talk to us. So remember, this is really, really surprising that we're able to find this. We have a couple of theories, but I don't want to be a conspiracy theorist up here of why this works. Please come find us in the back if you're interested for more information. But the ability to find super complex strategies like this really hammers home why we need an AI-driven solution to find new censorship evasion strategies. In addition to being able to find more complex strategies than a human could, Geneva is also incredibly fast. And here's a great example of that. In July of 2019, Kazakhstan launched its HTTPS man-in-the-middle attack, and this only lasted a couple of weeks. As soon as we deployed Geneva, it was able to find strategies within 1 hour to circumvent censorship. This is pretty groundbreaking because previously researchers would have to sit around, come up with new censorship evasion strategies, and then deploy those. But here we're able to find them instantly. All right, so I've talked to you about some kind of major improvements over prior work in the past, but nothing too crazy. Now I'm going to show you something too crazy. This is something that we're really excited about and think may be the future of censorship evasion. One of the main issues with censorship evasion research and tools as we know it is that they need help from the outside. Take, for example, something like Tor or a VPN, where you first have to connect outside your country before you can get to your final destination. The issue is there's a single point of failure there, right? Imagine if that Tor node goes down, or China comes in and blocks that Tor node, you can't get out to the real world anymore. Geneva doesn't have that problem. Geneva runs solely on the client. So we were sitting around one day and asked the question, what's stopping us from running this at the server? Now, take a step back for a second, and let's just think about the impacts that running Geneva on the server could have. Firstly, a client doesn't have to download any sort of software, right, because everything's running on the server. This is actually a really big deal because clients take on a pretty significant risk when they download something like Tor or a VPN. In addition, several clients can connect to one machine running Geneva at the same time, and we're able to subvert censorship on their behalf for all of them without them doing any work. And that's important because clients don't have to have any sort of technical expertise to run Geneva because they're not running it. In fact, a client doesn't even have to know that censorship evasion is going on because the server's doing everything. This really broadens reachability and accessibility for our end users. All right, so that sounds incredible, but there's an issue. When we were sitting around and thinking about this, we just kind of thought, you know what, there's not really a way that we could come up with a strategy that works here. And I'll show you why. So this is a waterfall diagram of a normal HTTP request. And we start out with the SYN, and ACK. This is just the TCP handshake, followed by the push ACK. A push ACK just contains the censored query. It's got the HTTP GET request or whatever it is. And that packet is then ACKed, and the response comes from the server. So from the client side, this is great. We have a ton of time to influence this connection. From the time that we send the SYN until we send the push ACK, we can do a lot of things there. But on the server side, that's not the case. The only thing we do is send this SYN ACK. And once the client receives that SYN ACK packet, it will immediately ACK it and send the push ACK. That push ACK has the censored keyword, and that's enough to trip censorship immediately. So we have to do something before that happens. This is a really, really small window here that we can influence this connection between the SYN and SYN ACK packets. And this packet doesn't have a payload on it by default, so there's not really much that we can do here. Luckily, Geneva doesn't know that this is an issue. It doesn't know that it shouldn't work. And please don't tell it, because we ran it and deployed it in China, Kazakhstan, and India, and we were able to find 12 strategies in those countries. Now, I'd love to take you through all of these strategies because we're really, really excited about them. Unfortunately, we couldn't get a 3-hour time slot from BlueHat, so I'm only going to take you through 2. So here's back to our waterfall diagram real quick, and then I'll bring out the strategy. This one works in China, and it uses something called TCP simultaneous open. So simultaneous open is a somewhat archaic TCP feature. It's basically the developer's answer to the question of what happens if 2 clients try to connect to each other at the same time by sending SYN packets. So we're first going to start TCP simultaneous open by sending our own TCP SYN packet, and then we're immediately after that going to send a corrupted SYN packet. This is just corrupted in some special way that we've crafted. So this packet then gets ACKed with a SYN ACK from the client, and I know what you may be thinking is that this looks a lot like the TCP turnaround strategy that we defined before. But that's not the case. Check this out. This works in China, right? And we know that China has long since fixed TCP turnaround. So why does this work? Instead, what we find is this is actually an off-by-1 error in the Great Firewall of China. When it sees the corrupted SYN and the SYNAC, it actually incorrectly increments the sequence number of its connection by 1, and that's enough to throw off the connection state and get around censorship. Let's go through another really cool strategy that Geneva finds, this time in Kazakhstan. This one we call the double benign get strategy. Basically, the way it works is we get a SYN from the client, and we immediately respond with 2 SYNAC packets. Now, it's a little wishy-washy here. We're basically doing our own things that aren't necessarily TCP compliant, and we're throwing a payload on this SYNAC packet. And this is something that Geneva kind of just explored on its own, because we didn't try to give it any information about the semantics of an HTTP connection, but it's still going to push the limits of what's possible. So it sends these 2 uncensored SYNAC packets. These are just benign GET requests that don't have a censored keyword or anything. And this actually performs a TCP turnaround attack, because now the censor sees 2 requests coming from the server, but it switches the minds of server and client, and that gets around censorship in Kazakhstan. Now, before I close up, I want to go over a quick overview of what we think the future of the arms race of censorship is going to look like. We get this question a lot of, we're releasing all these strategies to the public, and we're eventually going to release the whole engine for Geneva. So isn't that really just helping the censors in the long run? We think that we're actually helping the end users mostly. So by releasing Geneva to the public, we have the potential to fast forward the arms race for both sides. Geneva finds 2 different kinds of bugs. First, it finds bugs in implementation. These are things like the off-by-1 error that we found in the Great Firewall of China. It's kind of easy for these censors to come along and fix those low-hanging fruit bugs. But even if they fix them, we're still going to keep finding more. Geneva's really, really good at finding them all the time. However, the bigger issue is that we find these systemic design issues, these gaps in logic, we call them. And these are so much more difficult for a censor to fix, because they require a complete overhaul of their system. And that takes a really long time. Since Geneva is so fast, it's able to come up with these strategies really, really quickly and faster than a censor could fix them. So we believe that the logical conclusion of this arms race is that we're helping the end user more than anybody else. Thank you so much for coming to listen about Geneva. I'd love to see you guys in the back and talk more.